Good morning and welcome to the continuation of our summer webinar series. I'm very excited for the second topic in today's presentation, which will cover our completion optimization application, which is a fully customizable predictive solution that arms your asset and planning teams with answers to the multivariate problems that surround optimal development. It also helps you illuminate how well a strategy is performing relative to unbiased optimal outcomes. To start off, I'll provide everyone with a couple brief introductions. My name is Mike Whitney. I'm a product champion at Datagration. Also joining today, we have George Vonif, our SVP of Unconventional Solutions. George brings a wealth of engineering and financial knowledge from decades in the industry, both running companies and advising other companies on their own operations. I'll go ahead and provide a quick overview of what we'll be covering today, then turn it over to George to take us through the nuts and bolts of our workflow, including the utilization of customized engineering, geologic, and economic inputs, the training and validation of predictive models, and of course, the most important piece, how we can operationalize complex models to better inform drilling and completion decisions. Last, we'll answer any questions that do come up. Please throw anything into the chat that's on your mind in the comments area. And we'll also answer a few of the questions that we get most frequently. But anything and everything that comes to mind, throw it over in the comments. So now I'll briefly jump into the overall picture of Datagration and the PetroVisor platform. If you've tuned into some of our previous webinars or checked out our website, you've likely heard mention or read about our unified data model. Within PetroVisor, we utilize an open architecture data system that can ingest any disparate data set from across a business. It can then integrate the pieces that are needed for the subsequent workflows and calculations that we're going to run, such as what's needed for completion optimization, and ultimately fully automate data updates, those data integrations, model training, and population of data sets that are virtually live, and create those resources that are constantly up to date for your teams to make decisions on the fly. Built on top of our unified data model, we have fully structured and customizable applications that enable us to amplify our customers' analytical decision-making process through advanced engineering workflows that are very frequently multidisciplinary in nature. What you'll find is that we bring an operational improvement mentality into everything that we create, focusing on the most important KPIs and strategic initiatives that really move the needle for each unique business that we work with. Our platform and applications, especially as you'll see in the case of completion optimization over the next 20-25 minutes here, enable your greatest assets, the people at your company, to combine data analytics, machine learning, and physics-based modeling, and rich economic packages in a way that enables the inclusion of crucial internal business assumptions and data sets while maintaining a lean and unified view of whatever problem it is at hand. What you'll see today provides invaluable information for project-specific drilling and completion opportunities that takes into account completion dynamics, spacing decisions, cost variability, and geologic impacts, equipping everybody at a company with an easy-to-understand blueprint for optimal value creation in any price environment. Now I'll let George take it away to show us how PetroVisor implements complex multivariate modeling that removes the typical need for deep data science subject matter expertise and helps our clients make better informed and current decisions in their development programs. George?
Great. My name is George Vonif, and I'm going to walk you through our completion optimization workflow. We'll get to PetroVisor in just a moment and show you all the pieces within PetroVisor, but just to give a start, I wanted to give you a bit of an overview of the workflow itself so you can understand sort of how we approach this problem. Really, there are 7 steps that we go through within PetroVisor that are shown here on this graphic. And we begin by loading data and doing some QC on it. That's pretty standard fare, but the kinds of data we're bringing in include production data, completion data, geologic, economic, a variety of data sources that are a bit varied and disparate. Once those data sources are in PetroVisor, then we compute a variety of key performance indicators that are going to be used as we do these later steps to train models and to start making quantitative predictions. So these KPIs are things such as production indicators like an IP90 or a B90 or an EUR, a lot of geologic data, pH, TVDs, things like that, quite a few different KPIs that we compute. Then once we've got our data loaded, QC'd, and we have some things computed with that data, then we think about choosing a training data set. This is a data set in which we're going to try to predict well performance, production, from completion and geological parameters. And so choosing this data set can be very important. And obviously you tend to choose a single formation, maybe a particular fractured fluid, a geographic area of interest, etc. Once that's chosen, we then train models. We have both multivariable regression and machine learning models internal to PetroVisor. We can accommodate physics-based models as well. And again, these are models to try to make predictions of production and well cost from completion and geologic parameters. We then run a matrix of potential completion designs that could be thousands of individual designs. And for each individual design, we're going to forecast a 40-year production forecast and a well cost. For each of those designs, we also run economics. We have a full economics engine within PetroVisor. And that way we can begin to look at completion optimization from an economic and a decision-making standpoint. And finally, we have a variety of visualizations to help us see and absorb all that. One thing I want to point out just before we get into PetroVisor, this is a very automated process. In theory, we could automate steps 1 through 7 and never have any human interaction in between. I think that's a bad idea. The reality is between each of these blocks, we pause the process. We have places for the human to review, interact, QC, and maybe make some calls on some forward steps before that next step is taken. So this is not meant to replace an engineer. This is meant to enhance what an engineer can do by providing very sophisticated automated tools and providing that engineer with all the data and all the analytics in these intermediate steps to help have a very good process at the end of the day. With that, let's move over to PetroVisor. I want to start by thinking about, if you're doing completion optimization, what area or what formation or what situation are you trying to understand what an optimal completion design might be? The way we approach this from a human perspective and an interaction perspective is we like maps, graphs, and tables. And so we have a series of maps and dashboards to allow us to understand where do we have data, what kind of data is it, and how do we go about deciding what a data set can be. One of the places we start are with maps like you see here. And one of the things we compute are these polygons around every well called a Voronoi polygon. That is a polygon, they're non-overlapping, and it gives you a first order proxy of what the drainage area around a well might be, and also what the spacing between laterals or well bores may be. And what's really nice is we do this as a function of time. So we do it as of the times when the wells begin to produce and whatever neighbors they have producing, and then all the way into today. And so what this does, it gives us a nice mapping mechanism. It gives us some more KPIs to use in our analysis that begin to allow us to understand parent-child relationships. And then we can also use this as a capacity to come in and maybe start building data sets or selecting data sets through lasso techniques and whatever the case may be. And at the end of the day, what we're really trying to do is quickly understand, where do we have data? What kind of data do we have? Does it look reasonable or not? And let's figure out some data sets to let us make decisions and train our models on. Part of that process is looking at production data and completion data to help us understand our training data sets and what sort of data do we have to bring to bear. One of the big challenges with production or completion optimization is always, do I have enough data and do I have relevant data? So some of the things that we do within PetroVisor is forecasts are shot on every well, all producing phases, and those are done so that we now have not just what is a well making today, but what do we expect for wells to make out of the future. Why is that important? Well, as we want to start understanding our data sets, we can now take and use any of our parameters within PetroVisor and start to drill down through that data and understand, if I want to start looking at subsets of my data, whether it's by, is it a horizontal well or not, or what type of fracture fluid do I have, or what sort of formations are we in? This is a way for us to take a lot of data and very quickly start to drill down through it and identify those areas where we want to have our training data set to be drawn from. Part of the reason we like having these production forecasts in here is part of what we need to achieve at the end of the day are zero-time average production curves or production type curves to use in economics. And through our process, we automatically generate those curves for data sets of interest. And so as you go through this and develop the data sets that you're interested in, you can actually then see what some of these proxy type curves are going to be before you start normalizing those for completion parameters. Part of this process are obviously the completion parameters. And so that's a big part of it. The data set you're seeing here is all public domain information. So it does not include stages and clusters, but for demo purposes, I think it'll give you a pretty good idea of how we approach the problem. Once again, we have dashboards and data sets with lots of data in here, and we can once again start to come in here and drill down through that data. And for what purpose? This is to understand, where do we have data? How much data do we have? Is it varying through time? Are these data elements that actually correlate with performance of wells before we actually start doing the hardcore analysis? And once again, all this is set up so that we can then save this data into data sets that we're then going to use for analysis. So the goal with this is, how do I quickly come up with my training data set that I understand? I've got all these different visualizations that help me QC all that. Once that training data set is selected and decided upon, and normally this is a fairly quick process. Once your data is loaded, creating that training data set is minutes to an hour. It's not something you need to spend 3 days on. Once you get used to working with this, it's a very, very efficient process. And you oftentimes will have multiple training data sets. Hey, I want to try this data set over here that was only slick water. Maybe I've got another one we're going to use all fracture fluids. It's really designed to allow the user to do a lot of that kind of experimentation. Once the training data set is selected, we have some very sophisticated built-in processes to build models to try to take those inputs that you've selected and predict some kind of an output. In this case, we're typically taking completion and geologic parameters, and these are these X values, and selecting those to try to predict something production related. In this particular case, B90, that's the best 90 days. It's kind of like an IP90. We like it a little better. And in this data set, all we had to work with were TVD, lateral length, sand fluid, spacing between wells, latitude and longitude. Again, public domain data set out of the Frac Focus database. Lots of different formations here. So, at the end of the day, you'll have better and more data than this, but this is to give you an idea of what it looks like. And from that, we run it through, in this particular case, a multivariable regression process that we have. We do all the fancy things like collinearity reductions, Box-Cox, Box-Tidwell transformations to normalize distribution shapes, outlier detection removal, both single dimensional and multidimensional. Those are features you can turn on and off. And as a default, you leave them all on. It tests thousands of different possible models, and it finds the best model for you. And what's nice is then we show some graphics to show how that model, is it any good or not? So one of the graphics I like is observed versus predicted of the B90. What does the model actually predict versus what was actually there? And are we getting a reasonable fit? An R squared, in this case, of 0.85, which isn't bad given we don't have a lot of useful data in here. We also show how individual parameters influence the response variable. And these coefficients, this A and B coefficients, are the coefficients of the linear equation that model then uses. As a user, you don't have to sweat any of this. All you have to do is choose your inputs, choose which features, model features you wish to turn on or off, and you push a button. And it runs all the modeling for you, all the training. It creates this model, and it saves the name of it. And once that's done, we do this for the B90. We tend to do it again for EUR. And with those and a zero-time type curve that you've generated through your selection of your input training set, we're now ready to go and start evaluating what models might be and what completion designs might be optimal for going down the road. We do that by selecting a range of values for all the inputs and just doing do a matrix of all the permutations of those. So various lateral lengths, various sand and fluid intensities, various spacings between wells. And we can easily end up with 1,000 or 10,000 different permutations. Not a problem. We now have the ability, because of this model, to create an EUR and a B90 for every single completion design you wish to evaluate. And then separately, and we just don't have the time to get into it, we also create a well cost model in these terms as well. So now for every potential completion design, we're going to have a well cost and a 40-year production profile that is specific to that design. We do have a full economics engine within PetroVisor, and this is a standard 40-year monthly cash flow analysis, as you would normally see within any kind of a good petroleum economics package. And in here, we have all the usual suspects for inputs. We have, production taxes, operating costs, transportation costs, commodity price offsets, shrinkage. We can track down to purity products if you do fractionation of your NGLs. Standard but sophisticated oil field economics. And with that, we are able then to, for every one of these cases, not just predict what production might be, but now also compute what the economics would be from a standpoint of a rate of return or a PV10, et cetera. And this economics engine with PetroVisor is also used for all sorts of other things, such as base production evaluation, development optimization, things like that. But what's nice is we have that economics engine in, we generate this matrix of designs, and ultimately we then have some visualizations of how we visualize all the results of that. Because if I've got 1,000 different completions or 10,000 different completions, how am I going to absorb the results of that as a human being? So what we've done is we've created some interfaces in here to help you hopefully be able to come in here and understand, in terms of the input parameters and the kinds of things you'd like to optimize on, what should my optimal completion look like? And so we have an interactive set of screens here where we can come in here, and the user, as I'm doing right now, can just select what parameters they want to see, and the screens will update. There's about 1,000 different runs behind the scenes here that are feeding all of this. And this way you can have some graphical interfaces to let you see, for instance, on the right, fluid intensity, lateral length, looking at the B90. So that's like an IP90. Oh, the optimal treatment over here, from just a performance standpoint alone, would be over here in the corner. When you now dial economics into this and instead look at something like rate of return, that's going to show you, but if I'm trying to maximize rate of return, my optimal design is actually different than would have been if I'm purely looking at IP90. And again, this is meant to allow the user to come in here and just play around with the results and get an understanding of what are the combination of completion variables that achieve whatever it is you're trying to optimize. Again, typically it's rate of return or PV10. It could be other things. We also have summary tables down here to rank order things as you wish. So if you want to see the highest PV10 wells or the highest rate of return wells, or what are my wells going to cost? That's all part of these dashboards that are in here. So with this is really meant to allow you to come in here and have gone through the entire training data set, economic evaluation, and have the ability to come in here and start to understand what are the trade-offs as a function, for instance, of lateral length or fluid intensity or well spacing or whatever the case may be in terms of my performance. At the end of the day, what we have found in practice is oftentimes you will find that the optimal treatment may or may not be what you're doing, recently. And maybe this becomes a multi-year strategy to get out to where you think you want to go, because when you start to involve the operational folks in these conversations, you can show them, we want to end up over here. But from an operational standpoint, if you're someplace very different than that, you may choose to go there in steps rather than all at once. But what's nice is this, again, gives you the venue to begin to have those conversations with your ops folks, et cetera. So that's really all I had to show as quickly as I could, in our short time here, is sort of the process and some of the visualizations. And with that, I'm going to turn it back over to Mike.
That's great. Thank you, George. What we'll do is, and we'll keep looking at the comments here, chat, if any questions come in, but we'll run through a few of the most common questions that we get as we do have these conversations with current and potential clients around how they are currently making their analytically driven completions and development decisions. Yeah. So first, one of the very common questions that comes up is just simply how much data do I need to run the completion optimization workflow to get a model that is reliably predicting results?
Great question. And the correct answer is there's no magic number. There's no single number that's it. The number I recommend is 10 wells worth of data for every input in your training data set model. So for instance, if I had 5 completion parameters, things like lateral length, lateral spacing, sand intensity, etc. And let's just say I've got 2 geologic parameters, pH and maybe original oil in place. I would have 7 inputs that were then being used to try to predict something like a B90 or a DUR. So if I had 7 inputs, I would suggest that you try to have at least 70 data points there. So 70 wells worth of data. And if you had 50 wells worth of data, can you get a viable answer? Possibly. What you'll find is that typically as you have fewer data points, you'll still get answers, but you begin to lose confidence in those answers. So, and that's not that you lose confidence, it's that the confidence levels from a statistical standpoint just aren't going to be as strong. So the less data you have, you're just not going to be able to make as confident of statements as to what you can if you have more data. If you have 100 data points per input, wow, way better. That would be great.
All right. Next, here we go. We got a question. So George, for production forecasts or asset evaluation, can you create ghost wells and pads?
Sure. And I want to make sure I'm understanding what is meant by ghost wells, but you can absolutely set up wells that are meant to be, either arbitrary or, specifically in a certain area. So for instance, you could say, hey, I just want to pretend I'm going to have 10 wells over here in this pad and understand what my performance is going to be for those. Absolutely. So when you set this up, you don't have to tie this back to actual real live well locations. You can just set up fictional locations if you like. And then if you wanted to start to do sensitivities, for instance, within a pad, if you're looking specifically, example, for lateral spacing, I want to do some evaluations where I'm really training my models for different lateral spacings, which is typically something that you would set up and try to understand. This is a great technique for doing that. One comment I want to make towards that end, though, is if we're using empirical models, which in this example is what we're using. What do I mean by an empirical model? That means we're taking a regression model or a machine learning model, and we're training it on observed field data. In those models, there's no physics inherently in the model. And what I will tell you is I think those models are valid within the range of data they're being trained on. So for instance, if you had lateral spacings that went from 500 feet to 1,500 feet, and that was your training data set, I think you'd have good, viable, useful results using empirical models for lateral spacings between 500 and 1,500 feet. If you wanted to then go, oh, but I really want to know what it might do at 300 feet, be really careful. My suggestion is you need to embed physics, and you need to start then including physics-based models in the modeling process, which PetroVisor is set up to do. So that's not a problem, but it becomes a little more complicated because then you need to start including physics-based models, not just these empirical models.
Awesome. Thanks, George. Another question that came in. So can we isolate and compare co-completed wells to optimize timing or delay completion to, I guess, based on what we're focusing on, maximizing an IP or an EUR?
Yes. So we do, when we think of setting up these problems, the component of time and space is definitely part of our thought process. And so if you're saying that I'm going to complete 2 wells next to each other together, or delay, complete one and then later complete another one from somewhere else. Again, can we address this in this process? Absolutely. The real question is, though, am I using empirical models here to do that assessment, or am I going to have to go back to physics-based models? And the reason I bring that up is if you want to isolate, compare co-completed wells and understand the timing or delays in timing for completion and how that impacts everything, if your training data sets includes wells that have that range of outcomes, wonderful. The empirical models ought to be fine, unless you just have 2 or 3 of them. If you either don't have very many data points or you don't have any of those data points, then you've got to turn physics on to do that. And whether those physics-based models are analytical in nature or numerical 3D simulators, we have included those types of models in this process. And it works beautifully. So the process itself is designed to allow those models to do that. I will tell you, those physics-based models for the flow equations and for fracture propagation models are not part of PetroVisor intrinsically. So you would have to have those models yourself. And it's no problem. We're used to dealing with models and running those models. We're very experienced in that. So we've designed the process to incorporate those models, but they don't just come with PetroVisor itself.
All right. Thank you, George. Well, with that, I'll go ahead and just thank everybody for joining today. If any questions come to mind after the fact or makes more sense to have the conversation in person, please reach out, and either George, myself, or anyone you know at Datagration. And we'd love to have a conversation with you, kind of dig into the everything that we showed very, very quickly. We can dig into much further in a tailored conversation and demo that's centered around your company's needs. So please reach out and we can keep the conversation going. But otherwise, thanks again for the time, and everybody have a great day.
Great. Thank you.